Alright, welcome to Algebra 2, Module 3. Now we're in a new unit. This is actually going to be the logarithm unit. And the first lesson is exponential growth. Alright, so we're going to go and take a look at exponents in terms of growth and stuff. If you take a look here, they want you to solve each. I suggest pausing the video and doing these, and then coming back and follow along, make sure you did them right. So I pause for a second, give them a try, and see what you can do. Alright, so the first one, they both have the same bases on each side, 2 to the x, 2 to the 3. So guess what? The exponents, in order for the two sides to be equal, the x has to equal 3. It's that easy. Same bases, exponents got to be set equal to each other. Part B, you got an unwritten 1 here, so x has to turn out to be 1. That's pretty easy. In this one here, a little more work to it. You got 2 to the x. So how do you rewrite 16? Well, that's 2 to the 4th power. So if you rewrite it, your x is very simply equal to 4. If you go to D, okay, in D, I got 2 to the x. Okay, in D here, you got 2 to the x equals 64. Bring the 64 to the other side. 2 to the x equals 64. So that means 2 to the x is equal to 2 to the 6 if you change that in there, which means x is 6 is your answer. This one right here, bring the 1 to the other side, so 2 to the x equals 1. So you got to remember that 1 is the same thing as 2 to the 0 power. A little tricky there. So therefore x is 0. 2 to the 3x equals 64. So you rewrite it. This gets into a little better area. 2 to the 3x then equals 2 to the 6. And now we got to do a little math. Set the exponents equal. You got to do a little algebra. No big deal. 3x equals 6. Divide by 3. So your answer is 2. Same thing with G. 2x, 2 to the x plus 1 equals 2 to the 5th. So x plus 1 can be set equal to 5, which when you subtract 1 from both sides, you get 4. This one here is a little more challenging, as it says. You need to change both. So this is really a 2 squared being raised to the 2x. And this side is really a 2 cubed being raised to the x plus 3. So now the bases are both 2's. You just got to follow through. So this is 2 times, remember exponent rules. You multiply exponents, so 4x has to equal. Now you're going to have to distribute the 3 on both of these. So 3x plus 9. I'd bring the 3x over this way, subtract it, and you get x equals 9. A little creative on that one, but you guys can do it. Just getting the same bases and then set exponents equal to each other. Alright, so now we're going to basically, you can read the paragraph yourself and pause the video, but basically they're talking about E. coli, you guys have heard of before. Reproduces every 30 minutes, meaning the colony doubles every half hour. Okay, generation time will range from 12 to 16 hours. Basically, it's going to exponentially keep growing is what it comes down to. And they're talking about reasonable rates basically over a 24-hour reproduction period. Well, now we're going to do one here, and it says, suppose that we have a bacteria colony that starts with 1 bacterium and a population that doubles every day. So it's different from what we read above. What is the what function P can be used to model that bacteria every day? Well, you guys know exponentially that if we're going to talk about that, we'll talk about function P of T over time. And my initial bacteria is 1 times what is happening every day. The multiplier is doubling, so that's 2 raised to T would be per day. And that's the formula I'm going to do. Well, then they're going to ask you how many days will it take for the bacteria population to reach 8. So why don't we do a little bit of a table here. Okay, so if my time is 0, starting point, I'm just going to stick that in there. We know we start off with 1 bacteria. I'm going to squeeze that in as a little extra there. But if the time is 1 day, okay, what happens? I put the 2 in to the first power 1 day, and you get 2 bacteria after 1 day. Then if I put 2 in, I get 2 squared, which is 4. If I put 3 in, I get 2 to the third power, which is 8. And you'll see the pattern quickly and what's happening here. Alright, and we can keep this process going. Well, it asks how many days will it take for the population to reach 8. Well, here's your 8 right here. So how many days did it take? 3 days. How long will it take to reach 16? Well, you see that right there. So that's 4 days. How long will it take to reach 10? Uh-oh, 10's not in here. I don't see a 10. I go from 8 to 16. But the idea is it's got to be between 3 and 4 days that you get up to 10, don't you? So it's going to be between 3 and 4. So we will say 2 to the d equaling 10 happens somewhere between 3 and 4. Okay, so let's keep this process going with this problem. So it says we have basically a discussion right now. We know 2 to the d is somewhere between 3 and 4. It's called an underestimate of 3 and an overestimate of 4. Meaning I know I'm under a little bit by 3 and I'm over a little bit by 4. So how can we better estimate this? Well, we know it's between 3 and 4. So then why don't we go to the nearest tenth? Let's go a little bit bigger. Let's try 3.1. You plug it in the calculator. What do you get? I get 8.574. Well, that's not equal to 10. Plug in 3.2 and I get 9.190. Getting better. 3.3 is 9.849. And you could do this. 3.4 is 10.556. Sorry, my 10 there. So if I take a look at it, we want closer to 10. It's actually closer to the 3.3, isn't it? So that's taking it the next step, just playing by guess and check here. So now we know it's going to be 3.3 something, okay? So we now know it's 3.3 something, so my next guess is, hey, is it 3.31? Go out to the nearest hundredth or more. So I'm going to have you pause the video, and I want you to try a few and see what you come up with. So, knowing that I'm somewhere bigger than 3.3, it now looks like I'm closest to 3.32 I'm up to now. And that's my underestimate. My 3.33 is my overestimate. So now let's take it even a step further. Go another decimal spot. So I'm going to take another decimal spot. If I punch in the 3.321, I get 9.994. Boy, are we getting close. If I punch in 3.322, I actually get 10.001, almost on the noggin there. So now I can definitely say here, if I want to go out a few spots, that it is closest to 3.322. Alright, if I have to go out 2 decimal spots, I would cut it right at that, without a doubt. So my answer would be 3.32 overall to the nearest 2 decimal spots. What if we had wanted to go out to 5 decimal places? Well, if we had to keep going out, we would just keep squeezing, which means keep estimating. So I'll call it keep squeezing. You there. Until you can get to 5 decimal places. Until 5 decimal. So you just keep doing it over and over like a guess and check. Well, obviously this is going to bring something up that we're going to want to talk about eventually, which is there's got to be a system to deal with this and not keep doing guess and check. Alright, so to the nearest minute was the population of bacteria become 10. Well, we know it took 3.322 days where we left off. So you know that's 3 whole days. And then basically you're going to do 322 as far as dealing with all that. Which you got a lot of ways of doing. You can figure out how many minutes there are in a day. And you can take 322 over that and reduce that and figure that out so you can get you better. There is obviously a way of doing this coming up on the calculator. We used to do it in the old days on the table and stuff. I'm going to give you the answer for now, and we're going to talk about more in class today. But it really comes out to be 3 days 7 hours and 43 minutes. But we will talk in class on how we're going to get to that. And if you're smart, you know the name is called logarithms. We're eventually going to get there too, which will allow us to play with this stuff, okay? So that's what you got to look forward to in the chapter. That's it for the video lesson. Everything else we're going to get to in class. Have a good one.